Okay, this is David Zierler, Director of the Caltech Heritage Project. It's Wednesday, January 26th, 2022. I am so happy to be here with Professor Graeme Smith. Graeme, it's good to be with you. Thank you for joining me today.
Hi.
Graeme,
Thanks for
today
having me.
what I'd like to do is I'd like to start, if you can tell me, please, your title and institutional affiliation.
Oh, sure. I'm an associate professor of physics and a fellow of JILA at the University of Colorado in Boulder.
Graeme, how does that work in terms of your responsibilities? Is it essentially a joint appointment between physics and JILA, or do you have a primary appointment with interests on the other?
It's a little complicated. So JILA is a joint institute, joint between the university and NIST, and the fellows there are all either employed by the University of Colorado or NIST. And I'm employed by the university, and I'm a faculty member in the physics department, but I sit in a building which is different from the physics building. It's right next to it. It's the JILA building, and that's where my students sit. So I guess, yeah, I have responsibilities in both institutions.
In terms of your funding, does it all come from JILA, or do you get grants from NSF, other kinds of places that are funding quantum information?
I get it. Very little money comes. Well, no, okay. It almost all comes from grants.
What is the larger role that you see from JILA in this effort to build a quantum computer? What are they contributing to this broader effort?
Well, I mean, building a quantum computer is not the primary goal of JILA, nor is it. It's a side effect of much of the research that's going on there. But I think basically you will find nobody whose primary goal is to build a quantum computer at JILA. I mean, it's sort of largely an atomic and molecular, like an AMO physics institute.
Mm-hmm.
And much of the interests, to the extent that there is a sort of a vision, it comes from the overlap of academic interests and the interests of NIST. And NIST, of course, is very interested in precision measurement. And that's, I would say, is kind of like the primary driving thing going on. And then the reason people are involved in quantum information and quantum computing at JILA is that when you make an attempt to build really precise instruments, you end up doing a lot of things that are very similar to manipulating quantum information or even building quantum computers. But it's not that we're sort of like somebody's trying to make the next quantum computer with the largest number of qubits or something.
It's an interesting way that you phrase that quantum computing is almost like a side effect of what's going on at JILA. I wonder if you can explain, what are some of the research projects at JILA that, even in a happenstance manner, might actually contribute to some future scalable quantum computer?
Sure. Let's see. Well, I guess, okay, first I'll tell you about the experimental work. I'm a theorist, but there are really great experiments here. So Junyi, for instance, builds just like the best atomic clocks. And this involves kind of like managing the interactions between a bunch of atoms and kind of trying to make them as isolated as possible and to high fidelity as possible. And that sort of effort is kind of inevitably, well, I would say is moving towards kind of making a small quantum computer, like a highly controlled quantum system out of neutral atoms. We don't have anyone working on ion traps here at JILA, but at NIST, they have basically the best ion trap group in the world. And they, I guess, got into the business for building clocks, but it turns out they're also very, very good quantum computers.
Just as a snapshot in time, what are you doing, and what are some of the exciting developments in your group these days?
I'm doing a lot of things right now. So I guess so maybe we'll talk about this later. But I mean, when I get into this stuff, I was really properly an information theorist, doing communications problems, stuff like that, and I still do that sort of thing. But since coming to JILA, I have gotten more interested in, I guess, metrology problems. So one metrology problem we've been looking at lately is kind of trade-offs in sensing AC magnetic fields. So somehow strategies you use for measuring the strength of a magnetic field at one frequency are in some fundamental way required to be insensitive to the magnetic field at some other frequencies. So one thing, well, that's what I've been thinking a lot about lately, how to quantify and use sort of fundamental constraints on sensing to sort of better understand strategies for doing stuff like measuring very, very weak signals. So that's one thing. Another direction, well, I can tell you about the information theory stuff. It's still most of what I do. And that involves really trying to understand, given a noisy communication link, how can you use it through error correction to mimic a noiseless communication link? How many qubits can you send across a noisy channel? With what fidelity? What kind of codes should you use to achieve that rate? And how can you combine different resources in a way that is helpful for enhancing the capacities of the individual channels? So that's, yeah.
Now, your students, the graduate students and postdocs in your group, is their primary affiliation at Colorado or JILA, or how does that work?
The postdocs are affiliated with JILA, and the students are all affiliated with physics and JILA.
And in terms of instrumentation, of course, you're a theorist, but the world-class instrumentation at JILA, in what ways is that relevant for the questions you're after?
Well, I mean, this magnetic field sensing problem just came up like literally out of discussions with James Thomson, who is, very interested in understanding how quantum effects can be used to do better sensing. More generally, we have a lot of sort of, I guess, we have collaborations in the form of sort of large grants with a large number of PIs where, maybe what I would offer is some theoretical support for the more experimental parts, like maybe trying to figure out, are there ways we could do error correction experiments using the systems that people already have, or are there ways that we could perhaps run small algorithms in a meaningful way? So go ahead.
Sort of a broad historical question, given that you were at Caltech, really at the origins of IQI. Is your sense that over the past 20 years, interactions between theorists and experimentalists have reached a point where breakthroughs in quantum computing are much more feasible now than they might have been 20 years ago?
It's kind of a leading question. I'm not sure I would put it that way. I think there's been slow and steady progress on experimental efforts, and now they're getting to the point where they're genuinely interesting in terms of what they can do. 20 years ago, people were trying to get good 2-qubit gates, and they didn't have them. So, well, there's not a whole lot of, I guess. I mean, there's theory you can do in terms of modeling how they're trying to do their gates, but there's not a whole lot of theory that's sort of very deep that you can do on the computational capabilities of 2 qubits or something like that. Now people are starting to have bigger systems. They're still sort of noisier than they need to be, but they're getting to be interesting. And I think there's a lot of enthusiasm and hope for what that will mean for the future.
Just some nomenclature questions. You mentioned metrology. Just what is metrology?
Oh, it's the science of measuring things. So usually one would think of measuring frequencies, time, magnetic field strengths, charges.
So what are the most important measurements as they relate to quantum information and quantum computing? What are the units? What are the benchmarks?
Well, one thing would be sort of how precise. Well, basically, well, this is where the sort of the two interests slightly diverge. The most important measurement for an atomic clock is how precisely can you measure an amount of time, and it turns out that when you build a system that's really good at measuring time, it's a really good clock. You kind of have to have at least a pretty good quantum computer. The thing that's not really as fundamental, or sort of not as essential for clock measurements, is having two qubit gates. You can just think of the clocks are literally little atoms that spin around like this, and maybe it's not as essential to have really high fidelity 2-qubit gates for an atomic clock, but it is essential for a quantum computer. The other work here at JILA that I hadn't mentioned is really in superconducting circuits, which also are sort of a platform for building quantum computers that we have people here working on, but again, with more metrological focus. Like Konrad Leonard here works on superconducting circuits and builds like really great amplifiers that are good for sensing very small amount of noise, but they also find very small signals, and they also find use in readouts for quantum computers.
If we can imagine a Venn diagram, two really broad definitional questions. There's quantum information and there's quantum computing. What's the shaded area and what are the unshaded areas?
I mean, I'm tempted to say that the notion of quantum information science is sort of a bigger set, with quantum computing as a subset of it.
So
I don't know, it's probably controversial.
You would say then that all of quantum computing belongs in the larger discipline of quantum information then?
Quantum information science, I will put it.
Other nomenclature questions. Additivity. What does additivity mean?
Oh, it means when I have two separate resources and I have a way to quantify how good they are, I can put them together, and the sort of joint resource is better than the sum of the individual. It means that if it's additive, it means that the joint resources is equal to the sum of the individual resources. So like if I have $10 and I add $5 to it, the value is $15. So it means things interact in a very simple way. That's additivity.
And where might that slot in, or how do you use that as a tool for quantum information?
That is kind of so far has been a necessary property of communication channels in order to allow us to quantify their value for communication problems.
What about quantum annealers? What is that?
Oh, that's those are well, there's a historical question and answer and a technical. So the technical answer is they are devices that are meant to implement a version of the adiabatic quantum algorithm, and they are built without much regard for whether they can maintain quantum effects in them. So sort of a really great quantum annealer, which I don't believe people have actually made, would be something that sort of coherently sort of has high fidelity qubits and sort of you can use as a way to find the solution to some combinatorial optimization problem by gradually transforming the Hamiltonian of the system from a very simple one to a complicated one. And it's a way of mimicking well, the simulated annealing algorithm from the 80s, where you start with a random choice for basically the ground state of some Hamiltonian you're trying to find, and then you slowly reduce. Well, you sort of mimic some temperature, so you try to flip the spins to see if that gives you a better configuration than the original configuration you had. And you start at a high temperature and gradually ramp the temperature down. The hope is that finds the ground state of the Hamiltonian. So a quantum annealer is a version, a true quantum annealer is a quantum version of that algorithm.
And you mentioned that there's a historical side to this as well. How far back does this go?
Oh, not that long. Just historically, people started thinking about quantum computers when there was this company that wanted to have a quantum computer but didn't have a quantum computer, so they just threw together a bunch of stuff and said it was a quantum computer. And the algorithm they ran was the quantum annealing algorithm.
Graeme, the phrase quantum internet, something that you've worked on, is this something that's developing in parallel with quantum computers, or is it sequential? In other words, we can't really think about a quantum internet until we have quantum computers to create that network.
No, you can think about a quantum internet without quantum computers or without big quantum computers. You can imagine a network with, a few qubits here and a few qubits over there, and very limited operations that you can do here in each node, and they're all connected by optical fiber. You can imagine having a big quantum network with very primitive nodes. So you can imagine, well, yeah, given that you wouldn't be able to do very much computationally, I guess, but you may be able to do stuff like key distribution or generating entanglement for other reasons.
And your work on the mathematical properties of entropy, how does that fit in with your overall research agenda?
When you're trying to quantify the capacity of a communication channel, it's always in terms of entropies. So the goal really of my investigation of properties of entropies is essentially always to understand what's the how the sort of mathematics can be used to better understand the capacities of communication links.
Sort of an overall question to your research motivations. When for you and your lab are the most important questions simply fundamental research? And when are you thinking about practical applications that serve as a framework for the kinds of things you want to think about?
I think the lesson of information theory, and certainly of quantum information theory, is that if you pursue fundamental questions and really try to push the limits of what an information processing system could do, in principle, you inevitably sort of shed these extremely useful ideas that can impact practice, possibly in the future. Well, at this point, always in the future, but that can kind of guide our expectations and our hopes for what quantum technologies might become.
A question about thinking about practical applications, of course, there are major corporations that are involved in building quantum computers to the extent that it's a horse race, if that's the right metaphor, that companies like Amazon and Google, IBM, Honeywell, the list goes on, are all racing towards a quantum computer. To the extent you're paying attention to these developments and the different ways that each of these companies are going about that, does any one approach or technology or theoretical proposition seem most exciting to you or most realistic?
Yes, I would say if it's a horse race, the horses are all in the barn chewing oats. And the companies that recognize this are the ones that are most promising. So I would say Amazon is really doing things right in terms of basically, I mean, if I can say this, a bullshit-free way of doing things. Essentially, every other company is, over the past years, people became more and more comfortable using the word lie to talk about when people lie. I'm not sure I want to say that they're peddling lies, but they're peddling untruths, let's say.
There's a
Most
lot of
the
hype in this world, you're saying.
Well, it's not hype that I would say. I would say it's a deliberate misrepresentation of the situation.
Huh. That the field is it's a lot more, advances are not nearly as far along as these companies would have us believe.
That's correct, yes. We all know that a quantum computer that would have any kind of economic impact or any kind of use is ages away, decades away. And we all know also that but let me give you an example. I can't remember the company, but they're partnering with some car company to develop better batteries or something. And they made a huge announcement about this great new partnership. And, finally you dig deep enough into the article, they're running something they hope to be running something on 10 qubits or 12 qubits with hundreds of gates in order to solve this problem. Well, that's a very hard experiment to do, and I hope that they can manage to do that experiment they hope to do. It can offer nothing in the way of developing batteries for cars. The computations that small with that few gates are easily, I'm a terrible programmer. I could code it up and I could simulate it on my laptop. And the path to an actually useful quantum computer is much longer than what they're representing.
In this context, usefulness obviously has an economic component. What about some of the exciting prospects that a quantum computer might have for physics research itself? Do you see what you're doing, what's happening at Colorado, at JILA, as contributing to some of those questions?
Yes, so what I'm doing, I would say probably our work looking a little bit at error correction, both in the context of communication, but also in the context of computation, may well have some may well be helpful in that way. The work that Anna Maria Ray is doing with analog simulations using June's clock, basically, I think will have much more impact on physics in say the next 10 years than quantum computing efforts will. There's sort of this division between analog simulations and digital simulations. An analog simulation, well, you have this really great device. You don't have full control over it. You can't do an arbitrary computation, but you can give it the Hamiltonian that you're interested in. And you can learn a lot about that Hamiltonian in that system. I would say that path is going to be sort of much more promising than trying to do things on explicitly built quantum computers.
Well, let's take it back to a historical context. I'm very interested. So when you were at the University of Toronto, this is the very beginning, the late 90s, the early 2000s, this is the very beginning of people starting to talk about quantum information. Were you aware of those developments? Were you aware, even before you got to Caltech, of some of the things that John Prescott was thinking about at that time, for example?
No, not really, no.
Was quantum information a thing, even at the University of Toronto? Were you aware of it as a field at all?
I think Daniel Ladar was there in the chemistry department, and I might have gone to his talk, but it didn't interest me in any way.
So going to Caltech for graduate school, quantum information was not on your radar. It was not the motivating factor.
No.
What did you go to Caltech for? What was the game plan from the beginning?
From the beginning, it depends when the plan was. I mean, I hoped to do high energy physics, high energy theory, when I went there, but sort of in my final year of undergraduate, I kind of soured on that idea and began looking around for other things to do. And I poked around to all the graduate schools I'd been admitted to see who would sort of let me defer for a year if possible. I was going to figure things out. And many of them were kind of like fussy about it, but at Caltech, they said, sure, just let us know whether or not you're coming before September, and that's fine. So I thought, okay, I don't have anything else to do. I didn't have a good plan. So I said, I'll go to Caltech and, they'll pay me to be a TA and take some classes or something, and I'll figure things out there. And then there was a process, and so. But the flexibility of Caltech was basically it. It was like one other place said, okay, here's this formal thing you have to sign, and you have to let us know by this date, and this is how it's going to work. And at Caltech, they didn't care. If I was going to show up, I could show up. If I didn't feel like showing up, just let them know.
Now, was the IQI operational by the time you got there, or how did you become aware of the IQI?
It must have been operational, but I was really not paying attention to anything in the physics department there. I went and took a bunch of classes. Actually, my first semester there were no physics classes. I took some CNS, computational neuroscience classes, and I took a political science class, and maybe one other, I forget what. I was just really not planning to stay. But one of my friends, Ben Toner, he went deliberately to work with John, and I guess, yeah, he must have been already working at the IQI in our first year there.
And so what was the initial point of connection? What was compelling to you when you first got to know IQI and what was happening?
Oh, the thing I really liked was it was sort of an enormous group, and it seemed like the people in it were a lot of fun and very collaborative and nice. So that's really, and actually the science that they were doing, as far as I could tell, seemed, mathy and interesting. So I sort of poked around to see if there would be something there, and eventually there was.
And what did you want to work on when you got the sense that this would be your specialty, this would be your focus?
Let's see. I just wanted to find something I could do. But I talked to a lot of the people there. At the time, I don't know what it's like right now, but at the time, basically, there was lots of postdocs, maybe 5 postdocs or more, and you would just sort of go around and talk to them and see if they had any ideas you could work on, and then if something sounded interesting, you would do it. So I did that with a few people, and eventually I found some people to work with, Debbie Lung and Patrick Hayden. They had some problem that seemed really cool to me, involving random matrices and stuff, and a lot of math I didn't know, so I started working on it.
What was interesting? What were some of the big ideas at that point, or even the frontiers of knowledge, if you will?
Okay, so what was happening right then was people were, maybe let me say, okay, so let me say something about information theory. Information theory, do you know about information theory?
Sure.
Sure, okay, good. So the coolest thing about information theory to me is this random coding strategy. Like, if you take a classical channel and you want to know what its capacity is, you just kind of optimize over the input distribution. You can choose a code randomly according to that distribution, and that's just optimal. If you choose it of the right size, you achieve capacity, and you can't do any better. And people were learning right then was how to do this in a quantum context. It's not as simple. Well, it is as simple when I use words. The math of how that works, people kind of had been struggling with. There was basically Polovo, Schumacher, and Westmoreland knew how to do this for classical signals, for quantum signals, but classical messages. And people had feelings about how coding could work for, choosing random quantum error correcting codes, but hadn't really mastered until right at this point how to, say, show achievability of coherent information, which is coherent information is what you get if you choose random quantum codes, kind of in an analogy with classical constructions. So I think would have been in 2002, say, Peter Shor had shown or argued, Peter Shor gave a talk at QIP about the achievability of coherent information, and sort of people believed that was a correct argument. It hasn't ever been written up because shortly after that, Igor Devitak came up with a really crisp, rigorous proof. Seth Lloyd had sort of conjectured this value or this achievability of coherent information in the late 90s. But again, they didn't really have the tools to deal with random coding at that point. So people weren't able to establish it until, I guess it was 2002 Shore, and then 2003 Devitak had done the argument. And the other cool thing that was happening right then that is very connected is Debbie and Patrick and a variety of people. Debbie and Patrick and maybe some of the IBM crowd and Peter Shore had really begun to sort of show that when you look at a random quantum state where you have sort of fixed dimensions of, well, random bipartite state where you have fixed dimensions on A and B and some environment E, they really were, I guess, learning new things about the entanglement in such a state. This is the aspects of generic entanglement paper. I don't know if you know it. But.
What was the research culture like at the IQI? Were graduate students working with other graduate students, with postdocs? Where did people like John Prescott and Alexei Kitaev interface with students? How did all of that work when you were there?
Well, it was mostly graduate students working with postdocs or other graduate students. Both Kitaev and John had, they had their work that they were working on, and some people were collaborating with them on that. But if you were working with some other postdoc, generally he wouldn't be literally collaborating, but he would be aware of what was going on. And I guess the point of contact for everybody would be the weekly group meeting on, I forget what day of the week it was, but
I think it was Wednesday. I keep on hearing Wednesdays.
You're right. That was, then you had to present what you'd done that week. So, people would ask questions about it, and you had to try to make it sound like it had been productive and was interesting.
Graeme, what was the process for weaving all of these ideas into what would become your thesis research?
So for me, one of the biggest things, so what happened, I was working with Debbie and Patrick, and I got very interested in this additivity question for coherent information, which led to me doing an internship at IBM Research with Charlie Bennett and John Prescott. No, Charlie Bennett and John Smolin, sorry. That was sort of, I guess, more, that was kind of the thing that where my research started to actually work and things started to actually go well. It was sort of a group where I guess their style was very informal and very maybe qualitative, I could say. And that worked well for me. So we wrote several papers, and John Smolin became one of my best collaborators. And I don't know, I just worked with them. I worked with Debbie and Patrick, and I wrote a few papers. And in terms of thesis, it's literally, you staple the papers together and that's it.
What were some of the unifying themes from the different papers? If there was a big idea that motivated all of the different things that you were working on?
Sure. The big idea that motivated all of the different things I was working on was that, well, Igor and the others had shown the achievability of coherent information for quantum communication, and the non-additivity of coherent information really added a richness to the quantum capacity problem that wasn't present in the classical case, and in fact that we still don't understand. So the theme was, kind of coming at this non-additivity of coherent information from different directions. And I guess there was a little bit of additivity stuff too, showing, if we had this simplification, if we had this sort of, I guess, simpler form than the coherent information, we would be able to just have a clean additive theory instead of non-additivity.
In what ways did you see what you were working on as slotting in or responsive to some of the broader questions that your fellow graduate students, postdocs, what was happening at IQI more generally in those years?
Well, there were several exciting things. I mean, I think it fit right in the center of what Patrick and Debbie were doing on understanding, this properties of entanglement in high dimensional spaces, and more generally in sort of the project of I guess, turning Shannon theory into a fully quantum theory. I guess that's where it sat. I guess to me, there were a lot of cool things happening that I wasn't really doing, like Guy Vidal and Frank Verstraete were discovering or rediscovering DMRG and then generalizing it to PEPs and stuff like that. I watched that and I was interested. I didn't do anything in that area.
Graeme, what was John Preskill's style like as a graduate mentor? How often would you contact him? How hands-off or hands-on would he be? How did that work, that relationship?
Oh, extremely hands-off, except for the fact that you go to a group meeting and he's going to ask you what you've been working on. And you we felt very much like we had to have something substantial to say. 1 week, if you've done nothing, that's fine. But like a few weeks and you better have at least done a little bit of work. And he seemed to be paying attention and knew about that kind of stuff. When I was just starting, I kind of got stuck. I talked to a lot of different people and didn't really have any projects I could work on or I could get to work. I later learned Debbie and Patrick, as a joke, gave me sort of an extremely hard problem that's still not solved. And that didn't work either.
Which problem is that?
Oh, it's a kind of a Hamiltonian simulation problem. There's like a really nice clean answer for 2 qubits. We said generalize this to higher dimensional systems. And there's not a clean answer and it's not very nice. And you basically cannot solve it. But anyway, I was very, very frustrated. So I sent John an email. Of course, I sent one like multiple paragraphs or something like, can we meet to discuss some like maybe new directions I could work on? And we met and we said, well, what have you been doing so far, first of all? So I told him, and then he said, well, what seems interesting? And so I told him some of the things that I thought sounded interesting. He said, that sounds good, you should work on those. And I had been hoping, right? I show up, he says, solve this problem. I take the problem, I solve it, I give it back. But that's absolutely not how John worked. And I think it's really at a very extreme, well, at the time it was at a very extreme end of hands-off. But also at the time, if you wanted, like, he was very open to, like, he would take you as a student. That was another reason I joined his group, because like there was no, there didn't seem to be at least any hurdles. Like if you go and say, hey, I'm interested, can I work in your group? You'd say, sure, come to group meeting. That's the end of it. Many other people, you have to prove that you have some qualifications or capabilities, but that wasn't required. But the flip side of that was that sort of nothing was provided.
Looking back, I'm sure that has yielded benefits just in terms of you figuring out how to do stuff on your own.
Oh, sure. Yeah. And I mean, I it's not quite how I advised, but there's a touch of that. If people, there's a touch of that, because I mean, struggling through problems is kind of, you're gonna have to do it at some point.
Sure.
You might as well do it, I guess, early. The reason it did work though anyway was that the postdocs there were very happy to give you a problem. They just they wanted help with their work, and it was good for them to get it, I guess, to get experience mentoring and stuff like that. And I think it wouldn't have worked, and probably wouldn't have been done this way if there were no postdocs around.
To go back to this idea that, it's worse than hype in terms of how realistic, how feasible a scalable quantum computer is circa 2022, looking back to your Caltech years, what was the level of optimism or even exuberance about the creation of a quantum computer relative to now?
Well, it was believed to be hard. I would say that most of the people I knew and the sort of good, well, I guess what I want to say is the quantum computer isn't the point. The ideas are the point.
Mm-hmm.
And the ideas have already transformed physics in ways that are more substantial than anything that's going to come out of a quantum computer, as far as I would guess. Like, if there's no quantum computer ever, we still have a great new way of understanding physics that's basically providing a new language to describe stuff that we couldn't even have imagined 20 years ago.
That statement, what would be the banner headline that people need to appreciate in terms of the things that quantum information has pushed forward in physics?
Wait, the banner headline is in like, what are some, well, okay, how's this? Entanglement is everywhere. I mean, it's literally in everything. And, in condensed matter systems, well, people in condensed matter, some of the most exciting stuff on the theory side is just understanding entanglement structure in material systems. Of course, there's the high energy connection that I'm sure you're talking with other people about. There is, well, I guess the thing that I've learned that I didn't know at the time is just sort of the extent to which, it is really all entanglement everywhere, even now, like even in your everyday life. It's just a matter of kind of some of it, sometimes it gets hidden because of the way, we interact with the world. And I think that is far more interesting than estimating reaction rates of different kinds of chemistry problems. Sorry, just coughing.
Graeme, the idea that now we appreciate that entanglement is everywhere. So before 20 years ago, in the 20th century, what would we have said as an alternative? Entanglement is somewhere? It's nowhere? What's the distinction?
We wouldn't have said entanglement. I mean, it's just, we would have said the world is classical when it's macroscopic, and when you're dealing with atoms and stuff, you better use some quantum mechanics. But observers always collapse any kind of quantum states before they can get too big. Literally, I don't think I maybe heard the word entanglement once or twice when I was an undergraduate, and it just was not that relevant. And like, it was something that these annoying like foundations people who want to talk about what's the nature of reality always bring up. But I would have told you it's stupid. Like, use the wave function. If you have a mixed state, which is really part of an entangled state, you're doing it wrong. You should use the Schrodinger equation and use the whole just include as many systems as are required before you have a proper wave function. Like, it's, I don't know, maybe also that's me. I know there were people in the 80s and so on that had more sophisticated understandings of entanglement, but there weren't that many, and there wasn't much beyond qualitative discussions of how spooky it is and how weird it is. And it was considered like this thing that if you really forced yourself to you could get into this regime where you'd like violate a Bell inequality. And I guess that has some spiritual meaning or something. But like, I don't know, now I think it's, and I think, well, I don't know, even people who don't work on quantum information kind of would think it's crazy to try to talk about quantum mechanics without entanglement.
Interesting. Besides John, who else was on your committee? Well, my manager at IBM, I went to work at IBM after I was at Caltech. He described it as an inside job because John Smolin from IBM was there. Igor Devitak was at USC at the time, but he had just left IBM.
So I had 2 out of 5 from IBM, and really more my buddies than impartial observers. And then there was Oscar Painter, and he was my roommate's advisor, so I thought he's a good person to ask. And John, and then Bob McLeese was supposed to be on my committee, but had a medical emergency on that day, so he didn't show up. Actually, one thing that John, I was very impressed. Basically, John called the dean and got permission immediately that we could proceed with the committee, even though I didn't have the right number of Caltech faculty on it. Because with these outside guys, we only had 2 Caltech faculty, and you're supposed to have 3.
Right.
And I was worried. Oh shit, I'm gonna have to do this some other day. I'm so tense already. But it went fine. And then usually they're closed. Well, they are closed in the physics department, defenses. But my Debbie Lung was in town from Waterloo, where she had moved, and Aram Harrow just happened to be visiting, so he came too. So they were all there. They were both there.
Now,
also two IBM people.
What was the IBM postdoc wrapped up before you accepted to be at Bristol for a year?
Was the IBM postdoc?
Meaning you spent, it seems like it was almost like a gap year between Caltech and IBM.
Oh yeah, I was offered. I narrowed it down to I want to go to Bristol or IBM for a postdoc, and I went to Bristol and almost immediately decided I should have gone to IBM and got to work on going to IBM instead.
Now, was Bristol a center of quantum information? What was happening at that point?
Oh, it was amazing. Aram Harrow was a professor there at the time. Andreas Winter was there, and those are the 2 I went to work with. There was also Richard Josa and the other people who are still there, like who else? Noah Linden, Sandra Popescu. So it was sort of in the UK, it was the place.
But for you, what was the deciding factor where you realized you should have gone to IBM initially?
Oh, I see. Well, there was a bit of a culture shock for me in terms of just living in England and how things were expected to be done there. At Caltech, postdocs were extremely independent and more or less worked on what they want, and kind of were more or less senior people. At Bristol, that was very much not the case. So I knew that it would be like that. It would be much better. Well, I knew I would be basically an independent researcher at IBM, so I arranged to go there. In fact, when I was employed by Bristol, I spent a good part of the time visiting IBM. I don't know, it just somehow, it didn't work out very well in Bristol for me.
So did you defer your acceptance at IBM, or you had to reapply?
I think, no. I think they hired somebody else. No, I mean, I had to reapply. It was more like they had to, get another line that they could use, and that took some time.
And what was happening, when you get to IBM in 2007, what's happening in quantum at IBM? Is there a center? Is it a division? How big is it?
Oh, it's a tiny little group of really fantastic people working on what they believed to be, or the managers thought of as, I guess, very long-term, distant future stuff. So the people there were Charlie Bennett, David DiVincenzo, Barbara Turhall, and Sergei Bravi, who maybe you probably talked to him. And they were the staff members, and I was a postdoc, and I think Panos Alaferis was also a postdoc there at the same time, or maybe, I can't remember exactly how that worked, but and they had like one postdoc, and all these people. Oh, that's the theory group. There was a very small experimental effort, maybe 2 research staff members and a postdoc or something like that. And the theory group was amazing. There were people who were just constantly, they would have ideas, and you could just, I guess, you'd sit there at lunch and suddenly you'd have 3 things to work on, and you would go work on it. There were just a lot of sort of creative ideas being generated in sort of really abstract, in the information theory side, and also Barbara was doing some really cool computational complexity stuff too.
Now, as you said, this is far-reaching stuff. I assume that you're operating really in a fundamental research environment. There's no discussion about how any of this work might be applicable in an economic sense to IBM's mission.
Well, it was always required that you be able to tell a story about how there's a path from what I'm doing now to, possible impact on the business much later. But it was understood that much later meant decades, and it was, a small enough group that it was tolerated that we do sort of basically fundamental stuff, even curiosity-driven stuff, as long as it's in the general area of quantum information.
Graeme, I'm curious at IBM, given that IBM institutionally has been thinking about these things arguably longer than any other institution, I wonder if that was something that you felt when you got there, that there was a history to these ideas unique to IBM.
Oh, absolutely. Yeah, it was. There was a straight line from Rolf Landauer, who, he had Charlie Bennett as a postdoc who was still there and was actively involved in the research. And there was also a sort of, there was a flavor of work that was done, the sort of, and also sort of a way of working that was very, very different from what was going on. It was pretty non-technical and very conceptual, but ultimately underlying, ultimately there was math and physics underlying it, but it was really very much the sort of stuff that you could do a lot of it in your head and thinking about things in a somewhat different way. That was the thing that really made things work for me when I got there. And I kind of tried to adopt. And I would say, Charlie and Dave, well, yeah, I would say that's very much a reflection of Charlie and also of David, who had been there ages too.
Were there new ideas or approaches to quantum information that you were exposed to at IBM that you had not seen at either Caltech or Bristol?
That's hard to answer because basically from my 4th year at Caltech, I was in constant contact with the group at IBM.
Uh-huh.
And yeah, I guess the new approaches, the way I would think of it as it's sort of kind of playing games with quantum mechanics or quantum theory, really, to see what the structure looks like. And just saying, what if there are these 3 people who are trying to do this thing, and there's this wrinkle that this person's trying to get access to the thing, but the other one doesn't. And it really was a lot more about stories, about people just trying to play funny games. And that was I guess to me the difference that was there. People do, yeah, I think I'll put it that way. So I was thinking about how to basically, when I'm thinking, should I go to IBM or Bristol, I was asking Debbie, because she knows very well both places, or knew very well both places. And somehow basically, I asked something like, she was telling me, IBM, it would be a very good place to be. And I said, oh, good. Do they have different techniques that I could learn from them? Meaning ways of analyzing random matrices or something. And she just kind of stopped and said, no, they don't use techniques there so much as thinking about things in a different way. And I decided what I really needed was, I went to Bristol because I thought what I'm going to do is learn properly some rigorous new powerful techniques, and then I'm going to go solving problems. But that's actually, I don't like that model of working, it turns out. And Uh, Techniques are fine, but I think clean ideas are better.
Is this the first time you worked on cryptography when you were at IBM?
No, when I was a grad student, I worked on looking at non-additivity in BB84 protocol, and that's actually something that arose because Michael Nielsen had run a visiting fellows program for grad students. You just apply and you can go to Australia for 6 weeks or something. So like this was amazing to me. I had never been to Australia, so I went to Queensland, and lots of other people were there, and I met Joe Rennes, and he told me about cryptography and quantum cryptography and how it's sort of connected to coherent information. And we wrote a little paper together with John. So that's with John Smolin, rather. Smolin. And that's the first time I thought about cryptography.
When the postdoc was winding down, were you applying more widely, or that was a very easy transition into a staff position?
I was applying more widely. That was the, I don't know what we call it. It was the global financial crisis. So you remember there was this meltdown in due to housing and stuff like that?
Sure.
So I was applying, and Charlie and David were working to get me a job also as a research staff. And probably my first choice, I think, yes, my first choice was to get a job as a research staff member there. And ultimately it worked out, although it was much slower because of this financial crisis. IBM went into sort of a phase where they didn't feel like hiring people. But yes, I was looking for jobs. I wasn't very successful looking for jobs. Nobody was really hiring in this area at that time.
When you joined the staff, did that affect the kind of research you were doing?
Not really. I mean, a little bit, but there was still a lot of freedom to be working on things basically from a curiosity-driven perspective, with the understanding that it should be generally in a direction that would be valuable to IBM. It was still at the time, what you would generate, the value that you would generate was visibility for the lab and potentially useful things for later. That did begin to change around the time I became staff, maybe a few years later, and really transformed into, at this point, it's a matter of, are you helping the superconducting circuits experiments improve? So that's how I ended up over here.
Now, at this point, I'm as I always try to do, I'm establishing the historical narrative. Where was your sense of progress at this point? 10 years in, 15 years of the things that you had been working on. Where was the progress, and where was it simply new projects, new research endeavors that may not have necessarily been connected with what you had done earlier, and therefore the notion of progress might not have been relevant?
The progress that happened, I guess, somewhere towards the end of my IBM postdoc was we began to understand non-additivity. We began to realize, in my thesis, I had this formula that I thought this captures the quantum capacity, and I just have to show it's an achievable rate. And what we discovered a few years later, while I was at IBM, was in fact that doesn't. Well, basically, if that had been the correct formula, then we would have had a nice additive formula for quantum capacities, and the world would have been simple and beautiful. And the progress we made was to really discover that essentially all quantum capacities, all the different capacities for quantum for different kinds of communication are not additive, and instead, sort of better coding strategies than the random coding strategy seem to exist, or at least we don't have a good way to formalize the structure that needs to exist in quantum error correcting codes to make them really good. So non-additivity of quantum capacity was something that was really exciting at that time and closely connected to my thesis. Something that happened shortly after that was Matt Hastings showed non-additivity of Holovo information, which was even more surprising to us. And
why was that surprising?
Well, I guess we kind of there was some forms of non-additivity of coherent information that had already existed from the 90s that kind of told us, yeah, you're going to need to do better than random coding, and sort of pointed us, well, hinted at possible non-additivities of quantum capacities as well. Until then, there had not been any examples of non-additivity of Holovo information, and it was hoped that the Holovo information was in fact the classical capacity of a classical channel, and it was sort of there had been lots of numerical investigations that seemed to suggest that showed additivity for many cases. So there was a definite direction to the conjecture, and the conjecture that it was additive.
As Microsoft and Amazon, Google, and others started to jump into the quantum computer game, I'm curious how this registered for you or for IBM as these developments were happening.
Well, as these developments were happening, IBM was also growing substantially its experimental effort in superconducting circuits. And the things that we were, basically it was, the key thing I think I should mention is D-Wave. We talked about them before, but D-Wave was out selling devices that were super classical and saying they were quantum computers, and they seemed to be making money. And this was causing executives and managers to contact us and be like, hey, why aren't we also doing this? Like we heard that, basically the scientists had been telling them, no, it's going to take a long time. It's going to be a hard slog. And the superconducting circuits experiments were very primitive at the time. And then there became a lot of pressure from the top to really find some way to make this commercially viable. And that led to an uncomfortable dynamic where the more you would exaggerate about what quantum computers could do or when quantum computers might arrive, the more success you would have and the more resources you would get. So this led to rapid growth in the experimental effort at IBM as well. And also, I guess, the deterioration and perhaps elimination of actual science or fundamental science happening at the lab.
I guess then that this would not be unconnected from your decision to join JILA in Colorado in 2016.
No, it's not. No. I saw I had to leave and was very happy to find a position.
What has come of IBM's efforts since 2016?
Well, they've made a website where you can go and interface with lots of their experiments, and they've made really a large they have a large effort to convince people that they should be interfacing with that website.
Tell me about the opportunity at JILA in Colorado. How widely were you applying, and was the market better than first time around when you were a postdoc at IBM?
Yeah, the market was better. And the thing, I got to tell you about this fun thing we did at IBM. So John and I, we there were these people who kept telling us, hey, D-Wave is really eating your lunch here. And we would tell them, don't worry about D-Wave, it's not a quantum computer, forget it. And then they sort of didn't trust us in some sense. So we had to do more, if I told you my socks are a quantum computer, how much proof do you need that I'm lying? Not much, but they kind of demanded more and more. And ultimately, John and I started writing these almost it's well, sarcastic papers, let's say, polemical papers, where every time D-Wave pretended or had a claim that they had some quantum effects in their device, uh, we thought it would be fun to say, okay, we also have quantum effects in our classical simulation of balls and springs. And we sort of wrote a series of papers there that had some impact because they sort of influenced the way people began to think about testing, claims about quantum computers. What it convinced me was that sort of it's not a matter of people misunderstanding what the situation is in the quantum computing world. It's a matter of people really wishing the situation was different and simply pretending. Like, evidence is not going to matter in this discussion of quantum computers. And I bring that up because those papers that we wrote, while we wrote them basically as jokes, did contribute to some visibility for me, and I think did help me find a position. So the market was better when I went looking for a job, but also I was in a better position having done that research.
And to clarify, the joint appointment between JILA and physics at Colorado, that was baked in from the beginning.
Yes, this was, so basically, when we do a search here, the way it works is like, basically if you do AMO in the physics department, you're probably going to sit in JILA. Mm-hmm. JILA will run the search. There are extra people you will talk to make sure JILA will be happy to hire you, as well as physics. So the joint appointment was baked in, that's right.
Did you think about other industrial labs, or after that experience at IBM, you specifically knew you wanted to be in an academic environment? Or a university environment, I should say.
Well, I did two things. I thought about other industrial positions, sort of not in quantum computing. So I started looking, we were near New York. I thought maybe I can work at a hedge fund. So I started looking into that. Turns out I'm not a very good programmer, so they're not interested. And then I was looking exclusively for academic positions.
What was the game plan as you joined the faculty? You wanted to build your group. What were the big questions motivating you circa 2016, 2017?
The same one that in the information theory section, just capacities, understand quantum coding and how to build better error correcting codes for noisy quantum channels. That is sort of, I would say, a long-term, slow-moving thing that at the moment my approach is kind of finding better and better and cleaner examples of the effects that we're trying to understand. I hope that they will reveal ideas, and sometimes, they have revealed some ideas, but I hope that these examples which we've been sort of amassing are giving us a better idea of how to think about quantum coding that will let us really solve the quantum capacity problem. Now, that's not something I could count on happening. That's like a tough problem. So another goal I had was really understanding the information theory of networks, so multiple users interacting through some communication channel. And then I guess my third goal was I wanted to develop some things to work with. Like, I don't want to sit here and be in a vacuum. There's not there wasn't, especially then, a significant like straight quantum information effort. I wanted to develop connections and collaborations with people at JILA. So more metrology stuff.
Did you take on graduate students right away?
I hired a postdoc right away, and I had some graduate students by the second semester there, yeah.
And as you were putting together your own group, thinking about your postdoc at Bristol and IBM, being a graduate student at Caltech, what were your goals in terms of being a mentor, providing a framework for the next generation to start thinking about these things?
Well, I wanted to I guess, make sure that many of the ideas that that we had developed continued. Like basically, I wanted to make sure Shannon theory continued to be pursued in a sort of vigorous way. It's because it's hard and slow, and also not connected to not directly connected to corporate effort or to corporate what's
Interests.
the word? Yeah, interests, profits. Yes. I wanted to sort of make space for people to work on, I think, more important and more fundamental questions, and I wanted to, I guess, make sure that they were like basically put my students and postdocs first, rather than sort of try to milk them, like sort of grind them up and turn them into papers. And I thought quite a bit about it, and there's definitely a hint of what my advisor's hands-off approach, but I didn't fully take on that idea, and I don't think it would have been a good idea if I did. So, we collaborated, but I tried to make sure that people were able to follow their interests. Perhaps that's because I was leaving a place where I was certainly not able to follow my interests.
Graeme, I'm curious what interactions or opportunities you have to work with undergraduates at Colorado.
In terms of research?
Or teaching.
Well, obviously I teach with them a lot, and I've developed some courses we have a third-year undergraduate course on quantum computing that I put together with Alex Kola and Marie Holland here. And that's been a lot of fun. And I sort of gradually, very gradually, but my approach to teaching, to see if I could teach very well, was, I'm going to do advanced classes first and keep getting more and more basic to see if I can still manage like first-year students or something. And I'm doing the similar thing with undergraduate research. I'm sort of just beginning to do undergraduate research with the students because I feel comfortable now that basically I was sure I could handle a postdoc. I learned how to handle graduate students. At this point, I think I can manage undergraduate research as well.
I'm curious, teaching an undergraduate course on quantum computing, just as a sense of how mature the field is or your expectations, what grounding do students need to have in order to succeed in a third-year quantum computing course? What are the things that you expect in terms of knowledge or prerequisites?
Sure. We had a pretty hard, a pretty firm conviction that the prerequisites would be linear algebra, and that's it. So we have students from the physics department and students from the computer science department and from the math department. So that was, well, I mean, we totally screwed up at the beginning because they all had classes in linear algebra, but they didn't know any of the linear algebra they would actually need to do the class. So we ended up introducing into it, like a 2-week module, just basically introducing Brosinkets, reminding everybody about eigenvalues and eigenvectors and diagonalizing things and unitaries. And that's sort of it. So, I mean, I guess the prerequisite that we have is still just some class in linear algebra and a willingness to do this boot camp at the beginning.
Graeme, bringing the conversation right up to the present, just in terms of something we're all dealing with, the pandemic, has this been a productive time, just being more at home, having more bandwidth perhaps to think about these problems, or not necessarily?
It's been deeply unproductive. I have a 6-year-old and a 3-year-old, and my wife has a job that is, I guess, far more stressful and rigid in terms of the time commitments. So I have been surviving this pandemic only because of my students and my postdocs and collaborators. They are being productive. I am almost an observer, and that's all I can manage. I really, have discarded almost, well, I'm getting back to it actually. This semester I don't have to teach, and my kids, one of them is in school now, and next week the other one will be back to school, and this is my recovery semester. But it's been, I mean, nobody I know got sick, nobody's died. The coup failed, like in terms of the whole world. I'm doing pretty good.
Sure.
But it's the worst time I've ever experienced.
Yeah. Well, that's a great point as we close out our conversation. A few questions looking to the future. Hopefully, for everyone's sake, for you in particular, this will be a recovery semester. What are you looking forward to jumping back into? What's next on your plate?
Oh, okay, yeah. I've got an idea for an actual way to develop a coding strategy for quantum channels. And it's based on an old classical result of Martin on how to code for broadcast channels in a novel way. Broadcast channels is 2 receivers, 1 sender. That's relevant because a quantum channel just does have 2 receivers and 1 sender. The 2 receivers are the output of the channel and the environment that's screwing up all of the inputs. So my hope is, there is a qualitative analogy between broadcast channels and quantum channels. And I'm specifically going to try to develop a coding strategy based on Martin's coding strategy to turn it into a quantum coding strategy for quantum channels. So that's my excitement about doing something technical.
Who's funding that?
Who's funding that? First of all, I don't need somebody to fund what I think about, which is amazing to me. Let's see. It sort of overlaps with 2 of my projects. So I guess there's an ARO Muri on quantum networks that I have a small part dedicated to novel coding strategies. And then there's a career award I have from NSF that, non-additivity is kind of at the heart of it. So NSF and ARO. Let me think about what am I excited about? I am also excited that this paper on sensing magnetic fields has been in the works. Actually, I started it before I came to JILA. I met James during my interviews, and then I he sort of contacted me, and we started talking, and we had this idea 7 years ago, and gradually it came to fruition, and we managed to actually solve the problem. We were kind of stuck for years because I had the wrong conjecture. And luckily, one of my students went and did an internship at Honeywell and happened to be talking to them about some noise spectroscopy stuff. And they came up with a strategy that just sort of broke the conjecture and also made just everything fall into place. So I'm looking forward to, and the paper will finally come out within a month or so.
Oh, wow.
And we're looking at, what I want to do with that is look more into whether it can be applied. So the point of that is that there are strategies that kind of give you broad sensitivity across many frequencies that seem to outperform standard strategies people are using to do magnetic field sensing. And we're wondering whether that'll have applicability to axion detection. And basically there's a lot of physics I have to understand because, I'm less detail oriented, as I guess I emphasized with this idea of how IBM works. They do very simple things, but to know whether this is actually going to be a useful thing, we're going to have to do some details. So I'll learn some physics and see if this can be helpful with axion detection.
Is that to say that you might be jumping into the dark matter game to some degree? Yes, basically in a very distant way, actually we do have dark, Conrad here at JILA works on, I forget what the name of the thing is, but he builds the amplifiers for the dark matter detectors because qubits, it turns out, are pretty good, or at least superconducting resonators are very good sensors because what an axion would do is basically generate a little bit of extra magnetic field in there. And sensing that magnetic field is exactly what Conrad's amplifiers are good for. But that's really dabbling. But I think it could be. Look, if we find a way to speed up these searches, that would be amazing. And I think there's a non-zero probability, not a 50-50 probability, but a non-zero one, that we can actually offer some insight into how to do those searches. Finally, Graham, last question that will have both retrospective and a future looking perspective to it. In thinking about Caltech, IQI, IQIM at 25, I wonder if you can reflect a little bit about at the institutional level, reflecting on your own experiences, those of your colleagues, those who have passed through the program, those who are there right now. What do you see broadly as IQI, IQIM's contributions in all of these areas, quantum information, quantum computing, and all the things that people are doing there?
Well, okay, so early on, it played an essential role. It was the place to go for people if they were doing a postdoc. Like, you look at any of, well, not any, but like the postdoc market was, can you get a job at Caltech, or are you going somewhere else? And many of the best people went through there and really I mean, well, it was very important that it existed at the time, and the sort of work that got done in the early years was really quite amazing. Like, I don't know, you just look around at the people who are leaders now, and chances are you find they did a postdoc at Caltech at some point. There are other places that now do quantum information. One of the things it did, and I think John has done, is help make it a little bit more respectable. Well, it is more respectable. It's okay to do quantum information now. It's not crackpot stuff. and that was, well, that wasn't the case everywhere, but it was the case at Caltech when I was there. In terms of now, I think they're doing really, and I'm not sure the extent to which, you know, from the outside, I don't see quite how the division between like what Amazon is doing and what Caltech, IQIM is doing, you know, it's a little bit blurry. And I think that's an amazing thing too, because every other company is essentially going it on their own. And what Amazon is doing, I guess, is they're doing their program, and they're doing it in tight collaboration with really the best scientists. And it's I think it's demonstrating a different model for how you can approach doing industrial research, not just in quantum computing, but just overall. And I think it's ensuring a high level of integrity to the work that gets done, and it's providing like a model for other places that might like to do a similar thing. I think that's a really important influence they're having. Like, it's not that, like, you might say, hey, there's all this sort of hype and stuff. What I'm going to do is I'll do science. Maybe I'll work on something else. Or you can kind of drag the people doing the hypey things into being honest by working with them and showing them how to be honest and still make impact. And I think that's an important role that the IQIM is playing now. Kind of, I think also, well, I guess the students that go through there are also quite, at the time, like when I was there, students who went and worked with John at IQI, it was kind of like freaks and losers. Like, they tried something else and it didn't work. I would put myself in that category, but it was like very few people went to work there with this in mind. It was kind of a fallback, and you know, we maybe did interesting work, or maybe we didn't. But like right now, the best students in the world are clamoring to work right there, and I think making sure they're educated in a way that allows them to critically evaluate progress in quantum computing, claims about quantum computers. They have what's the word? They have role models who are optimistic and excited and honest as well. And that is something that, again, you know, seeing that you can be like gung-ho, really excited about a direction and still not fall in love with the idea so much that you can't see straight and you can't tell the truth, is really important for people who are going to be leading in this area in the future. So I think educating the students in a way that, well, in sort of the right kind of science is another thing that IQIM can do or is doing.
Well, Graeme, on that note, this has been a terrific conversation. I'm so glad we were able to do this. I'd like to thank you so much.
Great, thanks.